Well, so I will be taking care of the first three parts of this lecture series about what's called real Seiberg-Witten theory. And Ian Montague will be taking care of, well, these latter the last 2 days. So today, the first 2 days are basically, well, preliminary, so not quite about real Seiberg-Witten theory itself, but probably I should start from scratch like this. So first, the topic today is the Bauer-Frutter invariant. So what's, sorry, this thing. So the goal for today is to understand the following assignment. So what's input? So the input is a closed form manifold, always smooth, and together with the so-called species structure, which I will explain. So anyway, let me write. So this is closed and oriented and smooth. A closed, smooth, spin-C form manifold. So spin-C structure is a sort of a structure which is lifting to something higher from orientation, so which I will explain. And the Bauer-Frutter invariant gives you something out of this later. So the output is going to be, well, morally speaking, still. And like everything might be new for you, so I will explain the whole things in here. But anyway, the output is going to be a sort of map so this is some finite dimension vector space. So to be precise, I will make a compactification of this thing, which I again will explain later. So this plus mark denotes the 1 point of compactification. So this latter, the codomain is also some finite dimension vector space out of my form manifold, compactified. And so you get, for those domain and the codomain, for those vector spaces, I have some natural circle action. And you are going to get S1 equivariant. And well, I secretly put 1 point, which are base points, and based S1 equivariant based continuous map. And everything is up to suspension. So this output, if you are the first time to look at this output, so everything is unclear. So the goal today is to explain what do I mean by these terms. Okay. So first, so let me begin with, so what do I mean by spin-C structure? So here's the general definition. So first of all, let me define the group, so-called spin group. So this is a unique connected double cover, only non-trivial double cover of SON, which is, of course, a Lie group of same dimension as SON. And another Lie group you have to define is the so-called spin-C group. So this is simply taking direct sum with this spin group together with U1, the easiest Lie group, but divided by the diagonal action of Z mod 2. So acting on spin-C by the covering transformation. Okay, so spin N is a double cover of SON, so you have you have a natural covering transformation action by Z mod 2. And of course, Z mod 2 is sitting inside of U1, so you have also natural action on U1 by multiplication, and you take the quotient by this diagonal action. Okay? And so if I have oriented N manifold, X, so I say that a spin structure S on X is a pair, let's say P and psi, so where the P So one of the data. So P is a principal spin n bundle over X. And the another data, psi, this is an isomorphism. So first of all, so I have a principal spin n bundle, and you have natural reduction from spin n to also SON, right? Because the definition of spin group is a double cover of SON. So you have so natural projection mapping from spin n down to SON. So you can associate, you can change your structure group to SON using this homomorphism. And this psi is a data fixing identification from this reduced SON bundle to the oriented frame bundle. So of course, this is an isomorphism as SON bundle. So that's the only choice. So it has SON bundle. Okay, so far so good. So it's basically lifting a structure group from, this thinking about oriented frame bundle is basically equipping some orientation on your manifold X. And so I'm claiming that this structure of orientation lift to something higher governed by this spin n group. Okay. And spin-C structure is also defined pretty similarly. The spin-C structure, the notion of spin-C structure, just similar. Just simply use this spin-C n group in place of spin group in this definition. Okay. And in general, there is no canonical choice of spin structure or spin-C structure. And the amount of those structures are well classified by some homology. So here they are. Well, yep, but that's still right. So you have a natural map from spin Cn going down to SON just by looking at this left-hand side component and simply compose the canonical map from spin n to SON. Okay? Is everything clear so far? Right. So here's a remark. So if your manifold X admits a spin structure, then if we consider the isomorphism class of spin structures on it, so you can think of a natural notion of isomorphism class of the spin structure. So if you imagine the definition, so that's the correct definition, and you have one-to-one correspondence to H upper 1 with Z-mod2 coefficient. But, it's more not convenient to say that you have some natural action from H1, which is free and transitive. So in particular, if you pick one spin structure, then you have one-to-one correspondence from the set of isomorphism classes of spin structures to H upper 1 with Z-mod2 coefficient. And similarly, if your manifold admits a spin-C structure, which is always the case if your manifold is dimension at most 4, then you have similar correspondence from the set of spin-C structures on X, of course, up to isomorphism. You have, again, action from now H upper 2 with the coefficient. And again, this is free and transitive. Okay, so the isomorphism class of the spin structure and the spin-C structure are just governed by those homologies, cohomologies. Okay. So this explains what's the input for the Bauer-Futter invariant. So the Bauer-Futter invariant handles some continuous map, equivariant continuous map once you have a spin four manifold, oriented towards a four manifold, equipped with a spin C structure. Okay? Great. So now I want to make a theorem which I can rigorously state. So I don't know who I should attribute to, but let's say Bauer-Futter. Okay, first theorem. So this theorem says that, let's say you are given this the input data, spin C and closed and smooth for manifold. Okay, then there is the following map. So let me write so F, which is a map from some vector space, which is a combination of some real vector space and the complex vector space. Looking like this. But here I will explain the notation later. But this plus means a one-point compactification of the vector space, mapping to say Rn prime, there's some Cn prime. And again, I will make a one-point compactification. So where, well, first of all, so F is, I will explain this circle action also soon later. But this is S1 equivariant. And base, continuous map. And what are those dimensions? So dimension encodes the information of your four manifold. So if you take the difference for the complex dimension, say n minus n prime, so this is given by the following number. So this is 1/8 times, well, sorry, I have not explained this quantity, so I will explain some later. And C1 squared minus signature of your four manifold X. And so secretly, so this is, if you happen to know some amount of gauge theory, so this is a complex dimension, so sorry, complex index of the Dirac operator. So if time permits, I will explain, but well, so far you don't have to know about this. But anyway, something non-trivial is that this is an integer. So of course, this formula is divided by 8, so it's non-trivial, but it turned out to be an integer thanks to index theorem. And the other dimension, so I will reverse the order. Let me take m prime minus m. Okay. Then this is going to be the b plus over here for manifold x. So is everyone happy with this notation, b plus of x? This means the maximal dimension with a positive definite part of H2 with respect to the intersection form. All right? And this sigma denotes the signature. So this is a signature of the intersection form of your closed four manifold. Okay? And well, I want to write one more condition here. Sorry, right here. Let me continue. So one more last condition right here is that if you take circle fixed point set map, it turned out, well, I have not explained what's the action, but I will explain soon. So this actually is a map from the real part of the equation. This, and my claim is this comes from a linear inclusion. So it comes from some linear inclusion and compactified by 1 point. Okay, so here are the all properties I wanted to write. Let me add a couple of clarification about this theorem. Okay, so a couple of explanations. So first of all, so already appeared a couple of times, but this plus means a one-point compactification. So let's say V is a finite dimensional vector space. Well, over R or over C, I don't care. And then this V plus means a one-point compactification of V. Okay? One-point compactification. Right? So you have this vector space B, and you have point at infinity, and you end up with some sphere. Okay? And every time I regard this point at infinity as a base point, this is, you get it as the base point of this sphere. So Bauer-Futter theory is about pointed topological spaces, and this plus this point at infinity is always regarded to be the base point. Okay? And what else I have not explained? Okay, so the other thing I have not explained is this C1. Well, again, if you consider the set of spin C structures on X, say up to iso, you have a natural map mapping down to H2. So which assigns your spin C structure some cohomology element called the first Chern class of the spin C structure. And this is actually slightly different from the one-to-one correspondence I explained. So always you have free and transitable action of H2 on this set of spin C structure. But this is slightly different from that. But for instance, as far as your manifold is simply connected, or a little more weakly, if your manifold has no origin in cohomology, this is actually bijective. Okay, so in many interesting cases, this first Chern class is completely invariant for your spin C structure. Okay, and well, this notation C1 squared simply means C1 squared is just abbreviation of the evaluation of this C1 squared paired with the fundamental class of your form. Oops, sorry. Right. So is everything clear about the statement of statement? Say that again? Sorry, I just put here. Aha. Yeah, this is a characteristic element. So it's, yeah, no. Oh, yeah, sorry. So it's not bijective, but sorry, this is just, I'm sorry. So this is injective, and yeah, good point. So inside of this, so inside of this, you have an element called characteristic element, which is a cohomology class whose mode 2 reduction is W2. And so this gives you a bijection. This gives you a bijection if you restrict your polymer. Yeah, thanks for the correction. Any other? Oh, yeah, sorry. So I forgot to explain what these actions are. So let me explain that. All right, so this is not big enough practical, so I have to erase some part. Okay, so let me just erase this latter half of the statement here. Just I want to keep this thing. Okay. So what is this action? So here, well, I will act circle on R just trivially. So this is boring action. This is just trivial action. And the action on C, or copy of C, is just simply the scalar multiplication. So here I regard, of course, circle is the same as U1. The circle is U1 is inside of C, and you just multiply this complex scalar on C itself. Okay. So in particular, if you take, so whenever you have an equivariant map, you are allowed to take the fixed point set map. And if you take this fixed point set map, then this on this C, this acts non-trivially except for the base point in point at infinity and 0. So so it cuts down this map, and you end up with this map between these real vector spaces on which you have just trivial circle action. So what's so good? All right. I guess this explains what this theorem says. And so now I'm going to write another theorem, so which is a sort of spin version of this thing. So I have just explained the spin C setup, but the spin C case, you have something better. Okay. Spin case. So I'm going to write similar kind of action on vector spaces. So like one notation I have to introduce is this group called pin2, so which is a group which is the union of U1 and JU1. This is actually the disjoint union. So now this guy is sitting inside C directs some JC, which is identified with the space of quaternions. Okay. So now I'm going to activate. Okay, so I'm going to act this guy on, first of all, one real dimensional space. So let's consider a surjection, which is actually unique surjective homomorphism from pin to mapping down to the mod 2. So this is easy exercise is that if you are having such a surjective homomorphism going down to the mod 2, so this, oops, let me write maybe U1. So this U1 first component of pin 2 just mapping down to the trivial element, and this JU1 component, all of them mapping down to -1 inside of this mod 2. And I'm gonna let this guy act on one-dimensional real vector space, and to distinguish from trivial representation, which I will write like R tilde. This is like real one-dimensional representation. Okay, so acted by just a scalar, real scalar multiplication, or plus minus 1. Okay, so you have a one-dimensional real non-trivial representation of pin2 like this, and the other action I care about is the action on the spacebook quaternions. So now let's recall pin2 is sitting inside of quaternions. So this action is given by quaternionic scalar multiplication. Okay, so you just act pin2 on H using the quaternionic product structure. Great. All right, so now I can write down the second theorem, which essentially appeared in Furuta's paper when he proved 10S inequality. So let me have a spin closure for manifold, spin closed, and of course smooth for manifold. Then so I will write a pretty similar looking statement. So then there is a map F, which is from this Rm tilde, here some quaternions, 1 point compactified, mapping to Rm prime tilde, mapping to, again, quaternions, 1 point compactified, of course. And so this map is now pin2 equivariant. You have better equivariance than circle now. into equivariant, and everything is base. So this is base, and of course continuous map. Okay. And you know, the condition I was writing is again coming here. So for instance, if you compare this dimension of specific quaternions, this will be, well, now I switched to quaternions from complex space, so you're gonna divide by 16, and well, and one fact about spin structure is that there is no first Chern class, which is trivial in this case, so you gotta have this quantity as a difference. And again, so if you happen to know Dirac operator, so this comes from the quaternionic Dirac index, spin Dirac index. And similarly, I'm going to compare the dimension of the DL part, but again, take a difference from codomain to domain, then this is going to be the same. So B plus of X appeared again. And you know, the other conditions are the same. So if you take, well, inside of, or let me just say this. So inside of pin 2, of course, you have this U1. I sometimes write U1 and sometimes write circle. And so if you take this circle fixed point set, again, well, just cut down this map, and you end up with a map from, you know, again, just the same. So Rm plus mapping to Rm, well, pseudo, I should say. So this guy comes from linear injection. So this is the second theorem for the spin case. Is everything clear so far? Well, oh yeah. So this number is not invariant at all for the four manifold. So everything has to be up to suspension, which I'm gonna explain soon. Okay. So far, that's all statements like theorem 1 and theorem 2 are not talking about quite an invariant of four manifold. But what I have just claimed is you can extract some interesting equivariant map of this kind. Okay? But I will also talk about invariance later. So if you are the first time to look at this kind of theorem, so you might wonder how powerful those theorems are. But they are pretty powerful, actually. So for instance, from theorem 1, well, together with so-called Elki's theorem. Actually, theorem 1 is powerful enough to recover famous Donaldson's diagonalization. Well, probably I will give some exercise about this in the discussion session later, maybe today or tomorrow. And about theorem 2, this is essentially a core of the proof of Fruita's 10A theorem. Well, to be precise, for the first implication, you are going to use circle equivariant cohomology, ordinary cohomology theory. And for the latter, for the second implication, you need a bit more, so a little more fancier cohomology theory, which is pin to equivariant K theory. Okay? So applying slightly different topological machinery, you can get slightly different kind of constraint on your smooth form manifold. Okay? And we're talking about invariance. So I didn't talk about the invariance at all, but so if you pass to the stable homotopy, well, if you like, you should put more adjectives to make it precise, like S1 or pin to equivariant. And of course, base point has to be preserved every time. Stable homotopy class of my map F. It gives you an invariant of your spin or spin C4 manifold for this pair. And what do I mean by this stable homotopy is as follows. Okay, so let's say this stabilization. So what do I mean by this? So let me have a finite dimensional vector subspace of, like union of this real representation or and this complex representation. So this is finite dimensional subspace. Okay, and so in spin case, well, I guess you can expect, but in spin case, you should consider R to the infinity and quaternion infinity, okay, in place of this universe. And then you can consider the suspension of your map F by this guy, by which I mean you're going to take a one-point compactification of this vector space, and you make a smash product for both domain and codomain by this guy. Okay. Oh, sorry. Didn't write it this way. Okay. So this is the meaning of stabilization. And so by this sentence, I meant, so if you have two different kind of data to construct this map F, which I can explain a little bit later, so you might have different equivariant maps with different codomains, with different domains and different codomains. But so if you take a sufficiently large suspension for both sides, and if you allow yourself to move everything by equivariant homotopy, then you can have a notion of a stable homotopy class of your map F. And if you pass to this equivalence class, then that gives you an invariant of 4 manifolds. Yep. Oh, yeah, right, thanks. Yeah, everything is based, so I have to compactify this thing. Okay. Good. Other questions? Okay. So, well, I have just like 10 minutes or so, so just super quickly explain how this map is constructed. So maybe some detail could be put into the discussion session, I guess. Sorry, say it again? Oh, yeah. So by this I meant, well, circle acts trivially on this piece, and the circle acts on this piece by complex scalar multiplication, and you have induced restrictive action on this piece. Okay? So you have some equivariant vector space representation, 1 point compactified. You have some sphere having some circle action, and you make a smash product with that. Okay? Just trivial. Oh, yeah, good point. Yeah, so so the feeling is right. You just rotate this thing, and well, 0 and point out to infinity every time fixed. Okay. So how does this thing is constructed? So let's say I have a spin C structure. As I said, this corresponds to some principal spin C 4 bundle, which covers your frame bundle. And now, well, one fact about this is that spin 4 is actually same as SP1 times SP1, mapping down to SO4, which is regarded to be the SO of the space of quaternions by this correspondence. And so now I have three interesting representation of spin C group. So maybe at least I want to write down the domain and the codomain for the Seiberg-Witten map. So now you have interesting representation from spin C4. So here SP, so if in case you don't know, SP means the unit quaternion, the space of unit quaternions, which is diffeomorphic to S3. And you have three interesting representations called positive spinor representation and negative spinor representation and determinant representation. And well, so if you have an element inside of this inside of this, you can write by the coset consisting of two unit quaternions, one and one unit complex number. And you're going to act these things on, well, on Q, which now is in the space of quaternions, regarded as C2. And let me write it in this way. So this positive and negative spinor representations is defined by using this expression, either Q plus or Q minus corresponding to this positive or negative representation sitting on Q in the space of quaternion. And you're going to multiply this complex number lambda on the right. And the complex structure on this C2 is now regarded as a, you have a right multiplication. You act complex numbers on the right. Then you have a natural complex representation like this. And the determinant representation is simply taking the square of this last component, lambda squared. Okay? And associated these three representations, associated to my principal bundle, you have three vector bundles, S plus, S minus, and say L. By the way, C1 of S is simply defined by the first chancellors of this last complex line buffer. Okay. And one fact about the connection is that if you pick a U1 connection on the last line under L, well, I will define AL to be the set of all U1 connections on L. And you have natural correspondence once picking a connection. So let me pick a U1 connection, say, A node. And using this A node, you have a bijection mapping to imaginary valued one form of your manifold. Just by taking difference from your connection to A0. Okay? And now, so here is a Seiberg-Witten map. Well, several notation I just cannot explain because of the time, but well, you may ask me in the coffee time. So first, I will identify this space of one form together with, let's say, smooth sections of this bundle S plus. Using this identification, I will regard it as AL times these sections of positive spinors. And you have some mapping down to I omega plus together with the negative spinor bundles. And here, this new guy, this omega plus, which is depending on actually, sorry, I haven't clarified, but well, let me pick a Riemannian metric at the very beginning. Pick a metric G on your manifold. So this is necessary to write down the equation. And this omega plus means so-called self-dual two forms, by which I mean if you consider the Hodge-star operator, of course, which depends on Riemann metric G, it comes back to the omega itself. Okay? And you have some natural map from here to here called the Seiberg-Witten map. So the zero set of this equation is the solution to the Seiberg-Witten equation. So sorry, just for the time's sake, I can't explain those notation I'm writing, but something you have, some map, natural map you have, from here to here. And on everything, you have action of so-called the gauge group, which is super huge group like this, which acts on both domain and codomain in some way. And this map is equivariant under this gauge group action. And you're going to restrict this map a little bit. I'm going to restrict this map to the kernel of B star, which maps from one form down to zero form. And the latter, the remaining part of the equation are the same. So this is sections of positive spinors and self-deal two forms and negative spinors. You're going to consider this kind of restriction. And well, for simplicity, let me suppose B1 of my manifold is 0. So actually, Barber-Footer construction runs also for more general setup, just without this assumption, but let me just say this. Then my claim is that, sorry. Well, the zero set of this map is actually compact. Okay, so this is a crucial property in Seiberg-Witten theory. You have some nice compactness. All right. And so now what you're going to do is that you are going to write this equation splitting into a linear part and well, the other nonlinear part. So you just stare at this map and you just extract only the linear terms, which is this map L. And I'm going to take sufficiently large finite dimensional vector space on codomain, large finite dimensional vector space on the codomain, and let me put a V to be the L inverse of this guy. Okay? So then you have a map from here, which is given by L plus, I'm going to project the nonlinear part. So this nonlinear part might run to somewhere else. So I'm going to take a projection, some projection. A2 projection onto A prime, mapping to here. And this is my map, this finite dimensional map. Okay? So now let's come back to this picture. So this V is inside of I omega 1 plus positive spinors, and this codomain was inside of I omega plus negative spinor. Okay? And the circular action was inherited from this some mysterious action called the gauge group action. So inside of this gauge group, you have a constant maps. Okay? So you have just a constant map to U1. So which, of course, you can identify with U1 circle itself. Okay? And you have some inherited action of the circle in here. Okay? And it turned out that this F is actually equivariant under this circular action. And this crucial property, this compactness, you have to work a little bit in addition to this compactness. But it turned out that this is actually a proper map. So this is, well, kind of implication with quotation. So you have to work a little bit. But essentially, this properness comes from this compactness of the moduli space. And once you get a proper map from a finite dimensional vector space V to finite dimensional vector space V prime, you can compactify it continuously. Okay? So whenever you have a proper map, you can compactify it. Okay, so this is just last line I'm going to write. So you can compactify, and you get a map from V plus to V prime plus. So this is the map I was talking about. And in the spin case, which unfortunately I couldn't have a time to explain, but in the spin case, everything is upgraded to the pin-to equivariance. So this original map is actually invariant under some explicit pin-to action. And this finite dimensional approximation F also inherits that pin-to action. And yeah, so finally just end up with the map I was describing. Okay, so I think I'm running out of the time, so let me just stop here. Thank you. Well, if you allow yourself to have this trivial representation, so you have some merit in the stable homotopy theory, but the original Seiberg-Witten map itself actually do not involve this trivial representation. So well, you can add if you like, but this original map doesn't contain any trivial representation inside. Oh, yeah, B prime, so this guy, right? Yeah, so actually there is no, again, natural choice, but so the only thing you have to care about is that this part. So you have to get some proper map to get a continuous map between the one-point compactification. So to deduce this thing, so here, so I have not done the finite dimensional approximation for this statement. So you have to approximate this Hilbert space by large enough finite dimensional subspace. You might get some similar kind of information like this. So you have to make a good enough approximation. So at least this V prime has to contain the co-kernel of this linearization, linearize map, and also you have to take care of this part as well. But for instance, if you take a sequence of vector space, say, well, this kind of sequence for which if you consider the projection to this V prime and take the difference from identity, if this operator norms goes to 0. If you take a such sequence from some point, you can get this large enough subspace. So there is no like explicit. Well, you don't have to stick to explicit construction. So one way to construct this is you take, you know, like on here you have L star. So you have this self-adjoint operator. So you can consider the eigenvalue decomposition of this Hilbert space. So one way to say is that you're going to take very large enough this kind of eigenspace decomposition. So this is the eigenspace which, you know, whose eigenvalues is in between 0 and lambda. And if you take lambda large enough, then it gives you one choice of such a nice approximation. But in general, we don't have to stick to this.